Hey everybody, this is Larry. This is day 4 of the August Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join my Discord. Let me know what you think about today's problem. Path Sum 2. So I usually solve these live, so if it's a little bit slow, just fast forward, move ahead, whatever you need to do. Okay, so given a root and target sum, return one root to leaf, where each path sum is equal to target sum. A leaf is, okay. Okay, this should be straightforward in that the key difference between this and maybe a similar problem that I was looking for is that each path is from root to leaf, right? And that means that you can kind of implement things in the stack because, yeah, add an implicit stack where a depth first search or an order traversal type thing, or an explicit stack because the idea is that every time you see a node, you push it, you check, and then you pop it, right? So this is going to be linear time, and knowing that this is linear time because it is essentially an order traversal or a traversal of the tree, that I don't have to really look at the constraints because linear time is probably going to be fast enough. The only thing that may, like, variation that may change that is, for example, if there are a number of target sums, then you may have to play around with some ideas. But at least in this case, because of those two things, you can do it in linear time relatively straightforward, and it becomes an implementation problem. And here, there are a couple of kind of pitfalls, but in general, I think this should be pretty good. There are a couple of ways you can think about this problem. But and in this case, it's actually root to leaf. I think that was the other thing that I was actually double checking was whether, for example, intermediate nodes is good. For example, if it's 5, if the target sum is 9, is 5 plus 4, is that a valid path? In this case, it is actually not because you have to go all the way to the leaf. So let's, with that, let's go all together. And in this case, even though I said it's an order traversal, it is kind of a variation of brute force. And on that end, because you're trying every route to leave paths, it just turns out that there are at most n paths because there are at most n leaves, right? Which is not even possible. But no, in some you could do some math around that. But anyway. Okay. Okay. So n is at most 5,000. So like I said, it doesn't even matter. So let's go around it. So here, naming things is hard, but I'm gonna go. Let's just call it recurse. No, I just call things go as my default, but I want to be a little bit better here. So let's just call it partial path sum or something like that. And then you keep track of the node, the current path, and the current target sum. Well, you can do it either way. You could either return the current sum or the targets or the current target sum left by keep on subtracting it, right? So it doesn't really matter. Yeah. And then here, if node is none, we just return. I don't know. You shouldn't get to that. If no, it's not none in this case, and we want to check whether it's a leaf. One thing that I tried to be too clever in the past is but now I just be explicit about it because it's just do it. It's just simpler. And anyway, if this is a leaf, then if current sum is equal to target sum, then we do some magic with the path, right? So current path, let's just say we have a list of answers or paths, then we just do path.append current path. And one thing that's a caveat here, especially for Python users, but might depend on your language, and you'll go into this a little bit, but depending on how you construct this current path, you may be copying the pointer instead of the actual list content. So the thing that I would do here is just do this. And what this does is that it creates a new slice of a list in Python anyway, a new slice of the list that starts from the beginning to the end, essentially making a copy of the list. Anyway, and then we return in both cases. And then now if it is not a leaf, then we just do a recursion on the left and the right. Yeah. So partial path sum. In this case, you have node.left, current path plus let's see what, oh yeah, wait, oh, that value, I suppose. There are a couple, you can do it in two different ways, and you can, for example, do something like this. What is it? No that value, and then you do current path, or you could just do current path doing this. I think this actually creates a new list anyway, so I don't know how you feel about that per se. It does create a lot more space, so let's just do it the responsible way. And then here we have current sum plus no that value. And then here we have to pop off the thing that we just added. And then now we go to the right. Oh, actually, well, you could do it. I guess you can prematurely optimize a little bit because it's the same except for it's this, right? So in this case, obviously these things canceled out. So let's just do this. Yeah, I think we're good here. So now we just have to kick it off with power sum of root target sum. Oh no, this is 0, and then we return paths. So there are actually also a couple of alternate ways to do it as well. You can make it so that this actually returns a list, but then you have to go through it every time to as you go up to kind of reconstruct the path. Maybe that's better. I don't know. You let me know how you feel about it. But there are just different ways of doing it. Okay, well that's not promising. Perhaps some mistakes were made. I can't imagine this. Well, I mean, this actually would be right because it doesn't have any answers. But this is discerning. Did I miss something weird? That's weird. Do I have to do this, maybe? So I would imagine it complains if it doesn't. But I think I have some minor silly thing here. But okay. I mean, I don't think I spot anything obvious in my silliness. So yeah, let's print out current path here. Let's see if we at least get to the end. Okay, so we don't do that at all. Do I early terminate by accident? Dong dong dong. Do I at least get 2 leaves? Okay, so I do get 2 leaves. 4x. Oh, Oh, I'm just being silly. Basically, if I get to the leaf, I do not consider the current node value, right? So actually, okay, this is an edge case, but on the tree variety where I actually start from 0 instead of the root node. You can actually do this in a couple of ways. I think I did it this way for whatever reason, and yeah, just being very silly. Because then here, because we added the sum, so now it's good, but then now we also want to add to the current path as well. So if this is good, then let's just say path dot append no dot value, and then current path dot pop. Okay, so this should be good. A little bit sloppy here. Maybe we could have done it in a way that has better base cases, but let's give it a minute. I'm relatively confident about it. Every time I say that, I usually get it wrong, but this time it is accepted. As we said, this is going to be linear time because, roughly speaking, linear time. The actual expensive part of this, and I don't know that there's any easy way to avoid it, is actually, like we said, this is the number of current paths. I think given a full binary tree, you can imagine this log. No. That means that there's n over 2 leaves, and we reconstruct n over 2 leaves, and each path is log n, I suppose. In that case, 5,000. Log n of 5,000 is like what 20? No, not 20. 12. That is so 12 times 2500. I guess that. So that's the only thing that I worry about, and I'm trying to kind of be a little bit tighter about it. I mean, I already got to accept it, but if you want to consider, because this is the expensive part, and that's also the space as well, is that in the worst case, in the full tree, then you have n over 2 leaves. Is n over leaves the worst case? Yeah, I think so. I'm also trying to think about the other one where it's not binary, but and in that case, you can have a weird amount of space issue. In that case, it'll be 5,000. I think you can actually get it to a case where memory is actually n square ish. Given the time, I think should still be no. I think the answer is n square, and the case that I have here, and maybe this visualizer will help a little bit, is that in the worst case, I thought that a full binary tree may be the worst case, but actually, I think the worst case is actually something like, let's see if this works. I don't know if this is the right format, but yeah, so you have something like this, except for, oops. Don't know if I'm doing it right. Let's see. Okay, so something like this. I don't know if I'm doing this right. Okay, well, so now 1, 2, nope. And then now Okay, so something like this, right? So the idea behind this input set, okay, is that, well, they're going to be n over 2 leaves, but the space is going to be, and you can actually do this in a, I actually think I messed up with the target. Actually, well, if you put it all as 0, I think that would, because I think this is, yeah. So if this is all 0, then this can actually happen, right? Where then now your path is going to be n over 2, and then n over 2 minus 2, n over 2 minus 4, and dot, 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 and it becomes n squared essentially, right? So in that case, the worst case scenario for this is actually n squared, and n squared time, n squared space. So the nuance here is that the current path matters. If you did not have to care about current path, and let's say you're trying to return only the count of the number of paths, then it actually is linear time. But because you have to do this copy to kind of copy into extra space, and you cannot do better than n squared space in this case, because that is the number of, like, you have to allocate the space for n squared space anyway, because that's the size of your solution. So that is the lower bound for this problem in that case, right? So yeah, so it's linear time plus the output sensitivity, which is adverse n squared quadratic. Anyway, yeah, that's all I have for this one. Let me know what you think. Hit the like button, hit the subscribe button, join me in Discord. Happy Wednesday or whatever. Stay good, stay healthy, to good mental health. I'll see you later. Bye bye.